Today we'll show how to compute the magnetic fields for a long, straight, current-carrying wire. This calculation will have a lot in common with a calculation we did earlier for the electric field of a long, straight, charged rod, with the big difference being here we are dealing with sources of magnetic fields rather than sources of electric fields. Specifically, our starting point for magnetic field sources will be the Biot-Savart law for currents in a short conductor of length delta L. Now the key steps for carrying out this calculation for the wire are: divide this long straight wire into current carrying pieces, find the magnetic field for a typical piece using our Biot-Savart law for currents, and then applying superposition to sum up the magnetic fields for all the pieces in the problem. Consider a straight wire of length L with its center at the origin parallel to the y-axis. Let's assume a conventional current, capital I, is moving through the wire as shown. Let's break up the wire into short, straight, current-carrying pieces of length delta y, located at coordinate y. Now we're going to consider observation locations that are special. Observation locations that lie on a line that is perpendicular to the wire and passing through the midpoint of the wire. The x-axis is one such perpendicular bisector, so let's focus on a point located at coordinate x. The position vector r will tell us where this observation location is located with respect to a typical short piece of the wire. The distance from the short piece of wire to the observation location is given by the magnitude of vector r, which works out to be this. Now, vector delta B, the magnetic field at the observation location due to this current carrying piece of wire, is given by the Biot-Savart law, where vector delta L in this law is just delta y times y hat as written here. Rewriting this a bit, we can see that the direction of vector delta B is given by y hat cross r hat. Using the right-hand rule for cross products, we can see that vector delta B only has one non-zero component, the z component of vector delta B, and that component must point in the minus z direction. Additionally, the magnitude of the cross product y hat cross r hat is just sine of the angle theta between the two unit vectors. So here's the expression for the z component of vector delta B. We can simplify this further by using the geometry to find an expression for sine theta. We can insert this into our expression for the z component of vector delta B, and we end up with this. Now, let's pass over to the limit of very small pieces of wire. The deltas become differentials, and here is our resulting expression for dB sub z, the magnetic field contribution at the observation location located on a perpendicular bisector due to the conventional current, capital I, in the piece of wire of length dy. We're now in a position to do the final step. Sum up all the magnetic field contributions of all the current carrying pieces that make up the long straight wire. We integrate both sides of this expression, noting that on the right hand side we're integrating with respect to y from the bottom of the wire at y equals minus L over 2 to the top of the wire at y equals plus L over 2. The indefinite integral works out to be this, which we will evaluate between the two limits, and we end up with this final result. Let's discuss this result a bit. First, notice that the x-axis is not the only line that is a perpendicular bisector. There are an infinite number of such lines that are perpendicular bisectors for the wire. These bisectors lie in a plane that bisects the wire. So let's generalize our result a bit by replacing the coordinate x with r, where r now represents the radial coordinate that gives the shortest distance from the wire to the observation location in the bisecting plane. And our expression now represents the magnitude of vector B at the observation location due to the current in the wire. Next, let's consider what happens when the wire is very long, or equivalently, we're very near the wire. Under such circumstances, we can neglect the term r squared under the radical sign, and after some simplification, end up with this result. We see here that if we're sufficiently near the wire, or if the wire is very long, then this expression tells us the B field falls off like 1 over r. Let's also note that this result will still be quite good even if we're not on the perpendicular bisecting plane, as long as we're not too close to the ends of the wire. So that's the analytical calculation for the magnetic field of a long straight wire. Let's now do this calculation using a computer. We will follow the same steps. We start with the wire, here black in color, of some finite length broken up into pieces. We show the pieces with some separation to help us see each piece distinctly. The black arrow represents the vector dl, indicating the piece of wire we're focusing on at the moment. The direction of the black arrow is pointed in the direction of the conventional current, which is flowing from left to right. The red arrow represents the position vector for the observation location where we're calculating the magnetic field due to the piece dl. The total magnetic field that we've added up so far is represented by the blue arrow. As we click through the program, we add magnetic field contributions of other pieces until we have the full result for the entire wire at this particular observation location. Now, the nice thing about the computer is that we can repeatedly do the same thing for different observation locations automatically. So let's do that. At each observation location, computing the total magnetic field due to all the current carrying pieces, then doing it over and over for other locations. We can see a pattern. Notice the magnetic field is curling counterclockwise for the conventional current moving from left to right as shown here. This is a very general characteristic of magnetic fields. They form fields that curl around the direction of the current. There's a handy rule, another right-hand rule that we can use to describe this. Here's how this right-hand rule works. Encircle the current carrying wire with your right hand, making sure your thumb points in the direction of the conventional current. Then, if you look at your fingertips, treating them as your observation locations, you will see your fingertips point in the direction of the magnetic field. This works all the way around the wire as long as you keep the fingers of your right hand encircling the wire and the thumb of your right hand pointed in the direction of the conventional current. Let's try this out with the following question. We show two parallel wires here carrying current. The top wire has conventional current that is flowing in the minus x direction. The bottom wire has conventional current flowing in the plus x direction. What's the direction of the magnetic field at the observation location shown marked with an X? Stop the video and take a few moments to answer this question before you continue. Let's apply the right-hand rule to each wire in turn to determine the direction. First, the top wire. If we encircle this wire with our right hand, making sure our thumb points in the minus x direction, then when we place our fingertips of the right hand at the observation location, we see our fingertips point out of the page in the plus z direction. Next, do the same thing with the bottom wire. Encircle this wire with our right hand, making sure our thumb points in the plus x direction, the direction of conventional current. Then, when we place our fingertips of the right hand at the observation location, we see our fingertips once again point out of the page. So the sum of these two contributions will give the total magnetic field, which points out of the page in the plus z direction. That's it for this lecture. We'll discuss another current carrying configuration, a wire loop, in our next lecture.